Uh, Hi, everyone. I'm Puneet Agarwal, and today I will be talking about the features and capabilities of Innovium's flashlight telemetry in SONiC. Before proceeding, I wanted to extend my deep appreciation to the many individuals at Innovium who have made flashlight telemetry in SONiC a reality. Without their tireless efforts, this would not have been possible. Innovium delivers breakthrough innovation for data center customers. The Teralynx family of terabit switch silicon has been designed with a clean slate approach to directly address challenges in data center networks. We have a range of offerings that scale from 1 terabit up to 25.6 terabits, and our switches have already been deployed in high volume across all network tiers at top cloud customers. Teralynx devices all share common features that include high performance, low latency, and flexibility. And all switches provide extensible flashlight telemetry. The agenda for today's talk is broken down into three sections. First is Innovium's involvement with SONiC. Secondly, I'll talk about the Innovium flashlight telemetry in SONiC. And thirdly, I'll wrap up with a call to action. So let's take a quick tour of the software architecture of Innovium's SONiC system. If you look at this figure, at the bottom, we have the Innovium driver, which talks to the Teralynx devices over PCIe. This driver lives in the kernel space. In user space, we have the Innovium SI layer interfacing with a SONiC SI and using the Innovium SDK to talk to the Innovium driver, as well as to the actual device. The Innovium SDK is a clean slate SDK written from the ground up for high performance and reliability, and is common across the entire Innovium product line. Similarly, the Innovium SI layer is also common across the entire product line. SONiC on Innovium-based systems is already deployed in large data centers running live customer traffic. Innovium has a very long track record in supporting SONiC. In fact, Innovium is one of the very early enablers of 400 gig in SONiC. Our first SONiC release was based on SONiC 2018-03 in October 2018. Since then, we have made multiple releases, including SONiC 2018-11 and SONiC 2019-11. And we will be releasing support for SONiC 2020-06 and SONiC 2020-12 shortly. We have supported flashlight telemetry beginning in our SONiC 2018-11 release and in every subsequent release. Now let's take a look at Innovium's flashlight telemetry in SONiC. Before walking through various aspects of flashlight, I want to describe the key drivers for flashlight telemetry. As you know, network conditions have a large impact on application performance. For example, packet drops can result in requiring multiple retransmissions, which can reduce application performance. Similarly, even packet delays through a network can increase transaction completion times and lead to long tails and eventually impact the application performance. Visibility into such events is crucial for data center operators to be able to identify in real time what is causing the drops and delays, where are they occurring, what is getting affected, and how badly they are getting affected, and eventually take corrective action based on this information. Due to the high-speed nature of data center devices, all this must be done autonomously without needing any packet handling by software or microcontrollers. Also, to prevent flooding the collector with massive amounts of data, the telemetry information must be detailed but not overwhelming. In the Innovium devices, we provide flashlight telemetry as the umbrella for all telemetry engines that gather real-time information in the device and then send it to either a local collector or remote collector anywhere in the network based on user configuration. For packet drops, we have flashlights, buffer drop capture, also known as BDC. For packet delays, we have flashlights, high delay capture, also known as HTC. For flow path telemetry, we have flashlights, Innovium path telemetry, or IPT. These capabilities can be used simultaneously to enable deep analysis and insights into data center networks. In the next few slides, we will dive deeper into each of these capabilities. Now, before diving into flashlight, I want to first share some experiences with enabling flashlight in SONiC. For us, it was relatively easy to add flashlight in SONiC. The Redis database approach in SONiC made it simple to configure flashlight and to utilize the port and route information without needing any intrusive changes. Additionally, SONiC's comprehensive test suites enabled fast validation to make sure that we had not broken any other functionality. And SONiC really enabled fast delivery of flashlight to our customers. So let's dive deeper into the actual flashlight's capabilities. So packet drops can occur due to microburst, persistent congestion, etc. For example, at a top-of-rack switch, an incast event may occur when a scatter-gather event results in many servers delivering results to a common destination server simultaneously. In this case, the TOR switch containing the destination server will be receiving many high-speed flows, arriving to a single egress port, potentially resulting in packet drops. To assess what flows are being impacted as well as what flows are causing the congestion, one needs detailed visibility information about the actual drop events. Flashlight's buffer drop capture shines a light directly on packet drop events. BDC allows users to configure monitoring of drops during microburst events as well as persistent congestion. BDC delivers visibility information to collectors about who is causing the drops, who is getting affected by the drops, etc. BDC does this without overwhelming the collectors. For example, if you have 1 million packets getting dropped in 1 second, you do not want 1 million notifications going to the collector and overwhelming it. The relevant information is conveyed by BDC using a small number of notifications. Data center operators can decide what types of flows they want to monitor using BDC. For example, a data center operator may want to perform BDC only on flows between two specific subnets. And all this is user configurable. Now let's take a look at BDC in action in SONiC. Here we have a SONiC platform CLI. BDC supports many different modes. Most customers set up BDC in the microburst capture mode, where even if a short-lived microburst event occurs, BDC will notify the collector by providing a detailed summary of the event to the collector. In the example shown in the slide, the mode is set to the microburst capture mode. So now let's look at the collector setup. So once the BDC is set up, it will generate telemetry packets as needed without software or microcontroller intervention. The collector, as mentioned earlier, can be either local or remote to the switch, and it's purely a matter of configuration by the user. To configure the collector, the user specifies the type of destination. In this case, the destination is a local CPU. The user will also configure the traffic class, the destination MAC of the next hop, the source MAC of this device, as well as the IP address of the collector. Additionally, the DSCP and TTL of the telemetry packet is also configured. So now let's take a look at what is the information seen by the collector. So the collector really sees the details about the flows getting dropped at a particular switch in real time. Here you see 2 flows experiencing drops. Flow F1 has the 5-tuple with source IP of 10.10.10.41, test IP of 20.20.20.51, IP proto of 6, and L4 source port of 1031, and L4 des port of 2031. In this case, 152 packets for flow 1 have been dropped by the device. Flow F2 also saw packet drops. For this flow, 592 packets were dropped by the device. The F2 has a different source IP address from F1, as well as the L4 source and des ports are different. So this gives a good view of the flows getting dropped. Now let's go a little bit into more detail about the packets in a flow being affected by these drops. For example, for flow F1, the collector has detailed visibility information. The first drop packet for this flow was a 1500 byte packet, and the queue was 210 kilobytes when this packet was dropped. The next drop packet was a 64 byte packet, and the queue was 211 kilobytes at that time. The third packet that got dropped was a 1500 byte packet, and the queue was 208 bytes when it was dropped. So this gives you a great view of the specific flows getting affected by packet drops, as well as the packet length of the drop packets and the queue size at the time of the drop. There are many other configuration options and capabilities in BDC. This is just a small sample of these capabilities. So now that we have looked at packet drops in some detail, let's look at packet delays in the next few slides. As you well know, Congestion events do not always lead to packet drops. Brief periods of congestion and microbursts can cause queues to momentarily build up to cause spikes in delay, but not necessarily any packet drops. These delays can degrade application performance due to high flow completion times and long tails. To assess what flows are being impacted, what flows are causing the congestion, and also where these events are occurring, data center operators need detailed visibility information about the actual delays being experienced by various flows. So Flashlight's high delay capture shines a light directly on delay events. HTC allows users to configure monitoring of delays during microburst events as well as other congestion events. HTC delivers visibility information to collectors about who is causing the delay, who is getting affected by the delays, etc. HTC again does this without overwhelming the collector. For HTC, data center operators configure a delay threshold that triggers the telemetry collection. This delay threshold is completely user configurable. And data centers operators can decide what types of flows they want to monitor using HTC. This is all user configurable. In the next few slides, we will see HTC in action. I have skipped the configuration portion of HTC in the interest of time. However, it is very similar to how BDC is set up. The Htc collector sees information about the flows affected by delays. The collector can be running either on the local SONiC system or on a remote server or a switch running anywhere else in the network. In this setup, the user has configured the delay threshold to be 8 microseconds. This means that HTC will collect the telemetry information for packets that have experienced greater than 8 microseconds in delay. Here we see that there are 3 flows that have experienced high delay, F1, F2, and F3. Flow F1 came in on port 1 of switched 3002 and exited on port 3, Q1. F1 had 23 packets that experienced high delay, and the max delay observed is 13 microseconds. In flow F1, the average packet size for affected packets was 484 bytes, and similar information is available for each flow. Flow F2 and F3 have different source and destination ports relative to F1. Flows F2 and F3 have port 4 as the destination port, while flow F1 has port 3 as its destination. The max latency for flows F2 and F3 are both around 8.5 microseconds. Based on this data, we can see that on switch 3002, there is more congestion and delay experience on port 3 as compared to port 4. The collector has actually more detailed information about the packets in each flow. Let's look at the detailed information available at the collector for flow F1. The first packet that experienced high delay was a 64-byte packet which observed a hop latency of 9 microseconds. The second packet that experienced high delay was a 1500-byte packet that was delayed by 9.5 microseconds. The third packet that experienced high delay was also a 1500-byte packet that was delayed by 11 microseconds. Here we're actually observing the queue building up. From the information, we can infer that this queue could be draining slower due to the activity on other queues of the same port. So this gives you a very good view of the flows getting affected by packet delays as well as the size of the packets experiencing high delays. There are many other configurations, options, and capabilities in HTC. This is just a very small sample of those capabilities. So far, we have been looking at what's happening to packets on a specific switch. Data center operators want to understand how the flows are traversing the network and the congestion being experienced at various hops along the way. This is critical to identify the hotspots in the network. So operators also want to know if the path of the flow changes over time. So hence, Innovium developed Innovium Path Telemetry, or IPT, to address these requirements. So let's suppose you want to track flows between the bottom left server 1 and the bottom right server 2. You want to know the path the various flows take, as well as know what is happening at every hop along the path. You will need to monitor this information at a reasonable frequency to detect path changes and to know the behavior at each hop along the way. A critical aspect is that we want to perform this monitoring without modifying the actual packet being sent between server 1 and server 2. IPT in SONiC allows data center operators to discover a flow's path and collect periodic telemetry statistics for those flows without modifying the original packet. This periodic data collection enables data center operators to find hotspots in the network that could be driving up delays or drops across many flows. So IPT provides end-to-end network health statistics on a hop-by-hop basis. Data center operators can decide what types of flows they want to monitor using IPT. For example, you may wish to obtain path telemetry information only for RTP traffic between server 1 and server 2. Uh, Based on user configuration, the Teralink switch automatically generates probe packets at the first hop switch, in this case, 3006. The auto probe packets follow the same path as a tracked flow. No software or microcontroller intervention is needed to generate these auto probe packets. IPT provides the user control over the rate of the auto-generated probe packets. At each hop, these probe packets are stamped with the detailed telemetry information. The last hop switch, in this case 3007, collects the data from these probe packets and automatically sends this to the collector without any software or microcontroller intervention. In addition, IPT provides control over the rate of traffic to the collector at the last hop switch. So let's look at IPT in action in SONiC. The probe packets for flow F1 was first received by switch 3006 on port 1 and went out of port 2 Q1. This packet experienced a hop latency of 450 nanoseconds and saw queue size of 0. Then the packet went to switch 3005, where it was received on port 5 and went out on port 6 Q1. At this switch, the probe packet experienced a large latency of 6 microseconds, and the queue size it saw was 67 kilobytes. The packet then went to switch 3007 and came in on port 3 and went out on port 4 Q1. The latency observed was 465 nanoseconds, and the queue size was 0 again. Similarly, the probe packet for flow F2 also observed a large latency of 5.8 microseconds at switch 3005 on port 6 Q1. And the probe packet for flow F3 observed a similar large latency of 5.8 microseconds at switch 3005 on the same port, port 6 Q1. From the data, we can see that port 6 Q1 on switch 3005 is a hotspot and is affecting multiple flows. So IPT provides an excellent end-to-end view of what flows are experiencing at every hop along that path. So IPT can be used in concert with all the other flashlight capabilities. For example, after using IPT to pinpoint a hotspot, you could enable BDC and SDC to get deeper insights. However, to avoid missing out on information, customers typically enable all of the flashlight features at the same time so that the data is readily available upon identification of the hotspots. So this example demonstrates how SONiC provides flow path discovery and path monitoring in the network. IPT enables pinpointing hotspots in the network. So with the flashlight telemetry suite available in SONiC, you gain access to a wide variety of visibility features for data center networks. Buffer drop capture enables detailed visibility information about packet drops to understand what flows are impacted by drops, as well as what flows are causing the drops. After BDC is set up and configured, it operates autonomously and without any software or microcontroller intervention. High delay capture enables detailed visibility information about delays to understand what flows were affected by delays, as well as what flows were causing the delays. Similar to BDC, Htc also operates autonomously and without software or microcontroller intervention after configuration and setup. IPT provides data center operators the ability to identify flow paths as well as behavior at every hop. All flashlight features ensure that the collector is not overwhelmed. And all flashlight features can be enabled together to gain an in-depth understanding of what is happening in your network at any given time. So let's wrap up with some final thoughts. So we believe that the SONiC community would greatly benefit from flashlight telemetry. These features provide unparalleled network visibility into packet drops, delays, and in-depth analysis of flow paths and the ability to pinpoint hotspots in the data center networks. Flashlight provides these insights without any software or microcontroller intervention after initial setup. We plan to release Flashlight shortly to the SAI and the SONiC community. We are currently in the code review before release to community. So please contact us if you have any questions about flashlight telemetry in SONiC. Thanks for attending this presentation, and I'll be happy to take any questions.
Are there any questions? If so, please type them into the chat box and we'll address them. Okay, I don't believe we have any questions. Do we? Is Rupa, Shin, Omar, are you seeing any questions at all?